what do you do at UW, and why do you do it? Why do you wake up in the morning and decide that this is what I want to do?
That's a really good question, and I think that people don't ask scientists that enough. So I'm an atmospheric scientist, right? Study the atmosphere. I mostly study like the physical atmosphere, like patterns of winds, like the structure of the atmosphere. So that's like, you know, the temperature, pressure, how it's distributed about the Earth. I guess I always knew I wanted to do some sort of Earth science. You know, whether that was environmental science or atmospheric science or Earth science, I wasn't really sure when I got to college. I just knew I wanted to do something related to Earth science. And so I took a bunch of the different classes and ended up liking, you know, meteorology the best. So that was what my background was in, like weather forecasting. And then I felt like I didn't learn enough in undergrad, so then it was like, well, I guess I'll go to grad school. I'm still curious, and I think that's most of the reason why I do this, because it's fun, because I like understanding things, especially understanding the weather and understanding the Earth. And so I think I just naturally ask these sorts of questions, and I guess that's what drives me in research, too.
Brian, just, you know, where I left off was, I think the biggest question that I wasn't able to answer was, why is the ozone hole over Antarctica and not somewhere else?
Sure. Do you want me to start with that?
Yeah, I think so, yeah. Is that good with you guys?
Yeah.
Yeah.
Great.
Okay. So, I guess to understand, like, if there's an ozone hole, there has to be, you know, there's less of it there. So the question is what's the global distribution of ozone? And I don't know if you guys have looked at this at all, but basically ozone is lowest in the tropics and highest at the poles. And that basically goes like this. Most of the ozone production on Earth happens in the tropics. That's where the sun shines down on the oxygen molecules, breaks them up, and then they eventually, basically 3 oxygen molecules go into making 2 ozone molecules. And then there's winds that blow that ozone basically from the tropics towards the poles. And in the poles there's not much, you know, to destroy ozone. It's just really cold there, and it basically just collects in the poles. And so that's why in general at the poles ozone is higher. And so just like give you some sort of relative measure, it's basically 2.5 times greater at the poles than it is elsewhere. Basically, you get these substances emitted somewhere near the surface, you know, whether it's a refrigerant or whether it's from an aerosol that has CFCs in it. There are some other substances, and certainly there are natural sources of chlorine and bromine. It's just that humans, you know, from, you know, like the 70s on, really started emitting lots of these substances. And so they get up into the atmosphere through things like thunderstorms, lock these things up, just generally kind of the large-scale winds where there's rising motion in the atmosphere. And it really does take atmospheric winds to get them up there, because all these substances are actually heavier than air. So like CFCs are, if there was no wind, they really wouldn't be able to get up into the upper atmosphere. Like I said, it's things like the big windstorms that come and hit the West Coast, hit Seattle, those things will loft these chemicals up in the atmosphere, and eventually they get high enough in the atmosphere, up into a layer we call the stratosphere, where the ozone layer is, then they can start to work these reactions. And so scientists know that these reactions take place, but they don't really take place in fast enough to really make an ozone hole. So what do you need to get the ozone hole? Well, it's these things called polar stratospheric clouds. Sometimes they're abbreviated PSCs. And these clouds are way up in the stratosphere, so they're not like clouds you see outside today. They're very, very high, above like 10 kilometers. So like, you know, think about 6 miles. So imagine they're like 6 miles up in the atmosphere. So they're very high, and they're at these altitudes where there isn't much water vapor in the first place. So it's really hard to form the clouds. And so what you need to get these clouds to form are really, really cold temperatures. And so it just so happens that at the South Pole, there are temperatures cold enough to produce these clouds. And in the Arctic, the North Pole, temperatures rarely get cold enough for these things to form. And it's interesting because we knew about these polar stratospheric clouds at the South Pole in the 70s and the early 80s, and it really wasn't until about 1985 that scientists figured out that they were really the major driver of the ozone hole.
Is it possible for us to make ozone? Because I remember I saw something, it was extremely expensive, but they called it an ozone generator. I'm sure that was just a selling point, but can we make ozone?
Yes. Do you guys know about, like, what are the properties of ozone? Like, do you know, like, would you call ozone highly reactive or not very reactive?
Highly.
Yeah, so it's highly reactive, right? It reacts with lots of different other molecules and other compounds. So because it's so highly reactive, and it's made up of oxygen atoms, we tend to call it an oxidizer. So it's very reactive, and in fact, ozone at the surface is generally considered a pollutant. So there are high levels of ozone in the lower atmosphere where we live, and it's actually regulated by the federal government, ozone levels. So if a city goes outside of ozone attainment, they can get in trouble. We can make ozone. There are ozone generators. Sometimes if you have like an air purifier at home, it'll have like an ionizer on it. That ionizer is really just making ozone, and the ozone, the selling point is that it helps clean the air, And to a degree that's true, but you wouldn't want to like pump high levels of ozone in your house, and breathe that air, because it can destroy your tissues, like especially if you're breathing it in your lungs. Hey Kelly, office mate is here now. Everyone say hi to Kelly.
Hi.
Hi. So I'm just talking with this class about ozone. Oh, cool. So, anyways, can generate ozone, and it's generally bad for plants and humans, but I think in low doses it could be okay.
So one of the questions is there any way that we can replenish the ozone?
Oh,
yeah.
Not really efficiently. When you talk about the amount of ozone that you would need to replace up there, it's a lot, and it would be kind of counterproductive because the ozone-destroying substances are still there, so you would have to replenish it at a rate much greater than it's being destroyed. And so the better thing to do, and what policymakers have done, are institute kind of bans on ozone-depleting substances. So if we emit less, there'll be less up there to actually destroy. And so if we look at graphs of ozone levels, especially in the southern hemisphere, they've actually already started to recover as a result of these policy institutions that have been put in place, like the Montreal Protocol, for example. And then there were kind of agreements after that, too. We've also switched to substances called HCFCs. Have you guys learned about those at all?
Oh yeah, intimately familiar.
Yeah. Okay, great. And so so perhaps you know that like HCFCs tend to be broken down as lower levels in the atmosphere, in the troposphere, and so less of those ozone-destroying substances get up into the stratosphere. So they're not perfect. They're not a perfect replacement, but they're nice in that sense that they tend to be destroyed much more lower in the atmosphere.
One more question.
Like, worst case scenario, if all ozone goes away, how fast do we die?
Well, yeah, so there's these graphs that show, like, the cancer rates that would have occurred, like, if we had never instituted, these ozone-depleting substance bans. It would be pretty bad, because the ozone layer is, it's integral in a couple ways, right? So it blocks ultraviolet radiation coming into the planet, but it also acts as a greenhouse gas, and so if you take away the whole ozone layer, you probably, you reduce some pretty important greenhouse gases, and so the planet, probably gets colder too.
Thank you.
Yeah.
With the way things are going, would with the whole weather system we have now, would what would that look like in 10 years?
So what do you mean by that?
I mean, like, we've had severe droughts and typhoons and...
I get you.
Yeah.
Just due to global warming, I think if you ask that question, like, what could the next 10 years feel like, it's kind of hard to say.
Mm-hmm.
You know, there's always just climate variability. Like, if you look at the curve of global mean temperature over the past 100 years, you know, the general trend is up, but you see there's lots of little wiggles in that. And so it's always possible that you could have, you know, a colder decade. The next 10 years could be colder. But the general trend is going to be up as we increase greenhouse gases. I think on the ozone side of things, we should see recovery. And so it's potential that you'll see a recovery of southern hemisphere ozone by like 2050, for example, or even sooner, which would be a really positive, you know, result. We could see that where humans, you know, started to destroy part of the planet, and we figured out that we needed to stop something. We made some policy decisions, and then actually saw the result of those decisions. I think it would be kind of emboldening for people to see that. It's kind of similar to like thinking about like cleaning up local rivers or local lakes or cleaning up the sound. It's kind of like that sort of project, but on a much larger scale, right? When you think about global warming, you can't have, you know, if everyone in the U.S. got together and changed their ways, that would be a great step and it would help a lot, but you need global involvement on this. And so I think the recovery of ozone would be a good example of global, the people of the world coming together and doing something. So yeah. Okay.
Alright, I'm just going to ask you, earlier you said, you know, if you have too much ozone around you, it could be bad for you. And you were saying how, you know, air filters and stuff with like ionizers and stuff, they're basically just putting out ozone.
Right.
What would you think it'd take to get that to a dangerous level? I'm just curious now because I have one in each room of my house and they're all rated for a room like 5 times as big as they're in. So now you have me a little freaked out.
No, it's not something to worry a ton about. Like, I think that's just me not fully knowing, like with my own like little air filter design. But I think it would take a lot to get to really dangerous levels. Like you wouldn't want to like have that next to your, you know, you wouldn't want to attach like a tube to it, you know, and just breathe that air. Because it's certainly whatever's coming out of there, those ions are reacting with other substances in the air too. No, I wouldn't worry about that.
What can ozone pollution do to a person? Like,
Yeah, so can you talk about, ground ozone, what physically, you were talking about skin and respiratory, like what are some typical...
Yeah, exactly. You hit it right on the head. Like, yeah, so it's respiratory and skin issues. It can have a big impact on plants. So like, it's an issue like in California where there are lots of crops in the Central Valley. Ozone is produced there during the day, and it can have a detrimental effect on crops. And so, you know, regulating ozone is important.
You guys ozone satisfied?
Yeah.
If you guys have other questions, you can always email me.
Well, the whole idea of just getting you on Skype was this idea of like reducing our carbon footprint and saving you time.
Yeah. I had to drive to Everett last night, so this is interesting that I can just chat this way.
That's the idea. So, hey, thanks so much for your time. I appreciate it.
Yeah, thank you.
Thank
you. Okay, we'll catch you later, man.
Okay, great.
Take care.
Bye.
Okay, see ya.